Alright, so name of the reading now is correlation and regression. Now we would spend first 20 odd minutes in building the background. Then we would start answering learning outcome statements one by one. So at level one, whatever discussion we had at Quant, that was mostly a single variable discussion. That means we had one variable, returns on stock, or it could be volatility of a particular stock. And then with whatever data which was available, we learned to do various type of analysis. Right? So we calculated first, we learned to calculate measures of central tendency, which was mean, median, mode. Then measures of dispersion, which was standard deviation and mean absolute deviation. So we calculated all these numbers, and then towards the end we also learned to do hypothesis testing, mostly on mean and variances. At level 2 we would learn to deal with more than one variable at a time. So it could be either two variables or it could be three variables, and the numbers that we would really be focusing on at level 2 would be correlation and regression. And then again, first we understand what is correlation, we understand what is regression, and then we get on with the hypothesis testing. And so we start doing hypothesis testing for each one of them. So I'm going to build some hypothetical data originally just to work on the concepts, and then we will start drilling into each one of them. So you can write this with me. Let's say we have two variables with us today, variable X and variable Y. And the first thing we want to do is we want to see their relationship with each other. So let me assume some random values here, 10, 15, 20, 25 and 30. So we have values of X, we have values of Y. Values of Y here could be 23, this could be 33, this would be 43, this would be 53, and this would be 63. So we have some values of X and values of Y. The first thing that we would want to learn to calculate is a number called covariance. So we know that when we want to kind of gauge what is the relationship between two variables with each other, so one way of doing it is to calculate covariance. And then how do we do that? So step number one, we will have a total of X values, total of Y values. Then we will calculate an average values. So this would be 20 and this would be 43. So we have the average values of the data with us now. So once we have the average values, then we will calculate X minus X bar or X mean. So here it would be 10 minus 20, and in this fashion we would calculate all of the X minus the X mean values. These are X minus X mean values. In the same fashion we would calculate Y minus the Y mean values here. So which would be 23 minus 43. And once we have these two sets with each other, once we have these two values, then we will multiply these two. So we would multiply X minus X mean, and we would multiply Y minus Y bar or Y mean values. So that would be minus 10 into these values. So we have X minus X bar, Y minus Y bar, and the multiplication values. And once we have this data, then we can calculate the sample covariance. So sample covariance would be summation of this number. So let's calculate sample covariance. So sample covariance would be 500 divided by, tell me, n minus 1, which would be 4. population covariance in this case would be 500 divided by 5. We just take that n as it is. So we have values for sample covariances, we have values for population covariances. But I want you to write below this, unit of covariance is percentage square. Okay, so since we would be dealing mostly with percentage data, it is percentage square. So you can clearly look at this, gauge this from the formula that we have, that you are multiplying 10 percentage into 20 percentage, and therefore the final answer that you would have, that would be percentage square. Then make an arrow and say which is meaningless. Right, so that's one of the difficulty with covariance. It gives you values in percentage square, which does not really make much sense. Now look at the second difficulty here. Going to copy paste this data as it is. Now the only thing I'm going to change is going to have that 10, these x and y values in multiples. So now look at the x values and y values. They are 10 times of what values we had in the previous x. So let me call them as a and b now. In fact, let them remain as x. So we have x and y. If this value was 10, now this value is 100. If this value was 23, this value is 230. The calculations are exactly same. Now what is the covariance that we are getting here? So we have the covariances for the revised data. So we have sample covariance of 125. Here we have sample covariance of 12500. It has got scaled by how much? 100. And that 100 is because we scaled the first value 10 times and the second value 10 times. The entire data got scaled by, the covariance number got scaled by 100. So will it be appropriate to say that the relationship between second variable, the strength of that relationship is same as what was the relationship between the first set of variables? Yes. I mean, can I say that the relationship between these variables and relationship between these variables is exactly same? However, covariance is not telling us that, because covariance here is how much? 125, whereas covariance here is 12500, which means it is not necessary that if the covariance absolute number is higher, the strength of the relationship is higher. Are you following this? So what point you can write down below this? Larger value of covariance does not indicate stronger relationship. So this part I believe we had also seen at CFA level 1, so you would have some idea. Now what I want you to do is calculate sample standard deviation of x and sample standard deviation of y. .9 and 15.81. Now let us also calculate standard deviation for these two values. So here standard deviation would come out to be 79 and this standard deviation would come out to be 158. Again observe, can you see that that standard deviation also got scaled by 10? Correct? Because now imagine the formula x minus x bar squared. So since your values were higher by 10, the number got scaled by 10 and then under root. So we can make use of this property. The property is that whenever the absolute values are higher, covariance is higher, but at the same time standard deviations are higher. So we can scale those larger covariances with larger standard deviation, and that's why we calculate a number which is called as correlation coefficient, and that correlation would be calculated as covariance divided by standard deviation x into standard deviation y. In this case, that would come out to be a perfect 1. And the same formula here, correlation again would come out to be a perfect 1. That 1 is being calculated as 125,000 divided by multiplication of these two standard deviations. Okay, so write down the formula of correlation. We will write two formulas. First formula is sample covariance divided by sample SD1 into sample SD2. I mean, if there is a sample covariance between x and y, then sample SD of x multiplied by sample SD of y. Or alternate formula, population covariance divided by population SD of 1 into population SD of 2. Okay, so one of the online student, he raised a query saying, when you calculate correlation, which standard deviation should you use? Should you use sample standard deviations or should you use population standard deviation? The answer is it depends on which covariance you're using. So if you're making use of sample covariances, use both the sample standard deviations. If you're making use of population covariance, then use both the population standard deviations. If you'd imagine the formula, x minus x bar, y minus y bar divided by n minus 1 divided by x minus x bar square under root n minus 1. And then since the denominators are under root twice, that n minus 1 gets eliminated. And the formula turns out to be x minus x bar into y minus y bar divided by the root of those values in the numerator. Have you understood this part? Now, how do you interpret correlation? So below that you can write a point. You can say correlation is bounded by -1 and +1. So in this case, it appears as if the data is moving in the same direction. But let me play around a little bit. For example, if I make this as -15, then that correlation value has come out to be 0.75. If I further manipulate and make this as maybe -45, now the correlation value has come out to be 0.8. If I make this as 95, no matter what I do. So if I make this as -40, and then we have a negative correlation. Now the data is moving in the opposite direction. So positive correlation means data moves in the same direction, and negative would be data moves in the opposite direction. Then below that write down interpretation of correlation. ठीक है, so दो सेंटेंस लिखेंगे. First sentence, a correlation of 0.7 means (10% increase in variable x will result in 7% increase in variable y). And then make an arrow and say incorrect. A correlation of 0.7 does not mean, it does not quantify that strength of the, it does not quantify the magnitude of the relationship. Okay, so this interpretation of correlation is incorrect. What it means is, write down interpretation below that. Approximately, now this is not statistical interpretation, this is how I want you to think of correlation. Approximately 70% of the times data moves in the same direction. Okay, so correlation will never tell us if x increases by x percentage, then what would be the increase in y. It will just tell us what is the possibility that the y will increase. Are we alright with this? Now to quantify that magnitude of the changes, what we need to build is the regression. So with the same data now, I'm going to build a regression. Okay, so what I have here, for many of you, it is your first ANOVA table. Okay, ANOVA table is analysis of variance, and there is almost 100% probability that you're going to see this table on the exams. Okay, because this is kind of the core of reading regression and multiple regression. And in the past, at least in the mock exams, a lot of questions have been around how do you interpret these ANOVA tables. Okay, so we will slowly start making sense of them. But right now, I want you to focus on these values. So what values we have here? We have an intercept of 3 and we have a slope coefficient of 2. So what these values will essentially give you is an equation, and that equation is y is equal to 3 plus 2x, and of course plus a random error term. So now at times it could be a precise equation, at times it could be an approximate equation. But let us see with our data that we have. If you multiply this 10 with 2 and add 3, we will have 23 here, and then we will have 33, then here we have 43, 50 plus 3 53, and 30 into 2 60 plus 3 63. So the equation or data was plotted in such a way to give us an intercept of 3 and slope of 2. Another important number to be observed here is this number called r square. This r square essentially gives you what is the quality of your regression, and it is always to be read in percentage term. So an r square of 100% means that variability of x-axis is being able to explain 100% variation in y-axis. That means all your data points are on the line. There is no estimation error per se, and therefore accuracy of your regression is 100%. Is this okay? So what you would write down: simple linear regression equation, y is equal to a plus bx plus an error term. Okay. So below that you can say y is equal to, in our example, 3 plus 2x. Why do we have that error term at the end? Because now what values we have here are the historical values. What if now if I tell you what x is 40, then you will use the equation and you will say y should be 83. But then that 83 is a forecasted value which can have an estimation error. The actual value might turn out to be 82 or 81 or 85, and therefore a random error term attached at the end of the equation. Are we okay? Then write down below r square, which is also called as coefficient of determination. Now make an arrow and say indicates quality of the regression. Below that, for simple regression, in bracket, one independent variable. When you have just one x value, that's called as a simple regression. So for simple regression, r square is equal to r square. So the first r is a smaller r, which is what? Correlation coefficient. So r square is equal to capital R square. The second r is a capital R, which is coefficient of determination. So if you have a simple regression, then you can just square of the correlation and it will give you r square. Okay, let's play around with this data a little bit now. But let me scatter this data now. So instead of 23, I'm going to make this as 17. instead of 15 I'm going 33, I'm going to make this as 36. So I'm creating some error values here. Then let's make this as 35 or 36. This is 60, and let's keep this as about 58. So now we have revised value. In fact, r square shouldn't be so high, so let's keep this as 51 and this as 65. Okay, so now we have revised values of x and revised values of y. Using these, I'm again going to build a regression. Now say this. Now the intercept it is given us is 2.2 and x value it is given us is 1.94. Okay, in fact it would help if you write down this example. Okay, so what you do is first write down, so give heading would be example of simple linear regression. Example of simple linear regression. Simple linear regression. So write down x values and y values. Now let's insert these values in your calculator data function. So say second 7 and insert the x values and y values. Have you inserted these values? Now calculate what is the r of these values. Point how much? 8985.85. Okay, so let me also quickly do it. So correlation of these two value sets. Now one question that was raised, is this correlation for sample or population? So it is same. There is no difference between a sample correlation and population correlation. It's the same number. So once we have correlation of 0.85, can you estimate what should be the r square here? So r square would be how much? So square of this values 0.7226. Then in your calculator, in the second and 8, does it show you a value? That a value is what? Is the intercept. So a value is how much? 2.20. And then what is the slope value? 1.94. So an ANOVA table essentially would calculate the same set of values for you plus some additional statistical values which could be put to use. Now, if you look at the ANOVA table that we generated, it has given us same intercept 2.2. Is the slope same? 1.94. And can you also see the r square value, which is calculated as the square of correlation coefficient? Was your correlation 0.85? So here in the simple regression, multiple r and the correlation coefficient would be same. But as we go to multiple regressions, then this number would be different. And then what it gives us some additional values about this. Now observe this carefully. What we have is a residual output here. So this is observation 1, 2, 3, 4, 5. In fact, let me copy paste the actual data. So this is the actual data. Now your intercept and slope values are provided to us here. So these are intercept, these are slope value. Can we find out what is the predicted y value? Is it possible to find out what is the predicted y? Predicted y means the value that you would have predicted had you used that regression at inception. So that predicted y value would be 2.2 plus 1.94 multiplied with the x values. So these are your predicted y values. Are you following this? Yes, no? Has anything gone wrong? So these are your predicted y values. Now we would have we have the actual y values here, and what we have is the predicted y. So we can find out something called as residual, or also referred to as error, or at times also referred to as noise, which is essentially the difference between what is the actual y value versus what is the predicted y values. So it would be 17 minus 21.6, and these are all your errors. Predicted value is, if you were to use this equation of intercept and x value, then it says that y value is equal to intercept, which is 2.2 plus 1.94 into the x value. So observe this equation carefully. What we are saying is 2.2 plus 10 into 1.94. In the same fashion here, 2.2 plus 20 into 1.94. So each of that predicted value is essentially coming from your regression equation. Are you finding this difficult? You're just getting the values from the equation. So the idea here is that your line would tell you, the regression line, that these are going to be the values. These are going to be the values, but the actual values are these ones. So actual value and the predicted value, the difference between these two is referred to as the errors or residual value. Okay. Now what we will do is we will take square of those errors. We will take square of each of those errors. So we will say 4.6 raised to 2. So I'm just going to take square, plot them here, and then I'm going to add up all those. Sum of all the squared errors, SSE. So we have 361.1. Now this sum of squared error, one of the criteria for making selection of the regression line. So now I'm going to plot these values on a graph so that you have a better understanding. Now see, these are your actual points. Now let me keep this graph somewhere here. Observe carefully. When x was 10, here, what was the value of y? 17. So this is that point, that coordinate of 10 and 17. दिखाता है यहाँ पे. Then when x was 15, so we are somewhere here, y was how much? 36. So which is here, 15 and 36, so on and so forth. Now what is regression? You want to draw a line, and you want to draw a line within these points in such a way that sum of squared errors should be lowest possible. That's why it's referred to as optimal least square methodology. Now will you agree that within this there could be multiple lines that could be drawn? Out of these 5-6 points that we have, we can draw an infinite number of lines, right? So we can have a line like this or line like this. So then which line to be chosen as the regression line? That line which will produce lowest value of SSE, which is sum of squared error, would be chosen as the appropriate regression line. So this methodology is referred to as optimal least squared or OLS methodology. So hypothetically, if you draw a line between these, then the blue dot and the line, the distance between these two, that is what? Error. And then you square the error, and then you find out which line is producing the lowest squared error, and then that is the line to be chosen. Now in the ANOVA table, what was our total? 361.1. So look at ANOVA table. Can you observe this number? 361.1. So ANOVA table directly calculates that number for you. So in the residual section, when it gives you 361.1, what is the interpretation? This number is essentially the total of all the errors which are being squared.